Jai Hind to all of you. I am Priyanka Sharma, Assistant Professor, EC Department, AKGEC College, Engineering College, and I am going to cover the lecture on the fundamentals of electronics engineering subject, that is BC 101. In this, we are going to cover the topic related to Unit 4, that is digital electronics. In digital electronics, I am going to cover up the topic, the number system and the conversion techniques. So let us start with, so in number system, we're going to first start with we will start with the conversion of the number system. Before that, we first have to understand about the number system. What is number system? Number system is defined as basically the system of writing, and it is the way how we can express any number in any number system. Usually from the childhood or from the up to class 12th, we have studied about only the decimal number system, and we had studied about how we can express this. So if I'm taking the example of decimal number, that is 735, and we know its base is 10, it is written as an expanded form. It can be written as 7 multiplied by 100 plus 3 multiplied by 10 plus 5 multiplied by 1. This represents this 7 is the digit, 3 is the digit, and 5 is the digit at different places. So from this we come to know the last digit has ones place, last to second digit has tens place, and this has hundreds place. So in this way, by taking this places, we can write any number in any number system. So in decimal number system, we have the representation in 10 to the power form. So in this we can observe here 5 multiplied by 10 to the power 0. These digits are these digits in the digital number system are multiplied with their factor. This factor we call as weightage, or we can say it as positional weightage. So this will give you the complete number representation in any number system. So in mathematics notation, for representing the number of a given set by using digits or other symbol. So it provides basically the unique representation of every number and represents the arithmetic and algebraic structure of the figures. Like in decimal number system, we do the arithmetic operations like addition, subtraction, multiplication, division, having its certain rules. In other number system, we can also perform that same arithmetic operation with some conversion techniques. And it also allows us to operate arithmetic operations. As I told you, that we can perform arithmetic operations in any number system by taking the rule of that number system. Now, what are the different number system we have? As I told you, from the childhood, we had studied the number system, that is the decimal number system. In mathematics, or usually, we know about this number system, convey our information generally in decimal number system. This is being understood by all human beings. Now, the other number systems too, we have the different number system. I can include here other base system also. Other base number system. In this, so after decimal number system, we have other number systems like binary number system, octal number system, hexadecimal, and other base number system. What does this other base number system represents? We know that decimal number system is having base 10. This represents, base 10 represents number of digits allowed in that number system. The number of digits allowed will be starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 10 digits starting from 0 to 9 that is allowed in decimal number system. And we can also found in any number in decimal number system we don't have any other digits greater than 9. In binary number system, its base is 2, binary means 2, so it has only 2 digits, 0 and 1. In octal number system, its base is 8, then the digits allowed is 0, 1, 2, 3, 4, 5, 6 up to 7. Now the next is hexadecimal number system. Its base is 16. But in this case, we have basically we have the digits allowed from 0 to 15, but we know the numeric digits allowed is only from 0 to 9. So up to 0 to 9, it can be represented by numerical values. After this, the 10 can be represented as alphabets: 10, 11, 12, A, B, C, D, E and F. So A is represented as 10, B is represented instead of 11, 12, D is instead of 13, 14 and then 15. So in this way, hexadecimal number is a combination of numerical values and alphabets. Now if we talk about the other base number system, let's say it is X, any number system. So its representation, or we can say the digits allowed, is from 0 to X minus 1. Let's say if it is 7 base system, so the digits allowed will be from 0 to 6, 0, 1, 2, 3 up to 6. If let's say it is 12 base system, the digits allowed will be up to from 0 to 9, it will be numeric values, and after this 10, 11, 12 will be represented by alphabets A, B, C. So this is the number systems which we can refer. Now if you come to know about the decimal number system, as I told you, different digits has its some positional weightage. So this can be represented here. So and this system is also called as positional value system. So if we represent 734, the value of 7 is hundreds, and value of 7 is tens here, value of 7 in 207 is ones. So it can be represented by their positional weightage, as I already told you, 10 to the power 2, 10 to the power 1, 10 to the power 0. Why this is 10 to the power? Because its base is 10. So we can, if we generalize it, any number system, for any number system, the positional weightage will be equals to, the positional weightage is equals to base to the power n, base to the power n. So if the base is 2, its power will be taken. Now this shows the weightage of each position. So ones place has its weightage 10 to the power 0, last one is 10 to the power 1, 10 to the power 2. In digital system, instructions are given through electric signals. Variation is done by varying the voltage of the signals. So having different voltages to implement decimal number system in digital equipment is difficult. So decimal number variations cannot be easily implemented in digital number systems or digital equipments. So for that purpose, many number systems are used, and that can be easily implemented for digital circuits. Now, so for implementing the digital circuits, we have different number of systems, and the first system that we are going to use is binary number system. This is the easiest way for varying instructions through electrical signals. That means if we have to give the high voltage to any digital circuit or system, high voltage is represented by higher value. So it can be taken as logic 1, or and it can be said to be as on state. And if we want to transmit the 0 signal, it can be transmitted as low voltage, and it can be treated as the off state. So on is represented as 1 and off is represented as 0. 0 is actually not no signal, but signal at lower voltage. We can say it is not exactly 0, it can be any voltage, 1 volt, 1.5 volt, or it depends upon what threshold value I can take. So lesser than threshold value, we will treat it as 0, and above threshold we will take as 1. So there are two digits 0 and 1 in the binary number system. So we can say in binary number system, each digit of that number is called as bit, and each binary bit has its own positional weightage that is represented by in the form of power of 2. So the last bit has the positional weightage 2 to the power 0 and it is called as lower significant bit. And higher bit of this number, if let us take this example, in this least bit is 0, LSB, this is called as lower significant bit, and this first bit is called as most significant bit. This is the most significant bit. Binary number system, if we calculate this by using the positional values, this can be calculated as, if the binary value is 11010, so each bit will be multiplied with the positional weightage taken in the order of 2 to the power in the increasing order from 0 to the power 0 value, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and this will give you the equivalent decimal number. So this 26 decimal value can be transmitted as 11010 in digital, and it can be transmitted in the logic of high voltage and zero voltage in the digital circuits. So if we going to calculate these bits in the computer memory, it can be represented as 1 byte as 8 bits, 1 kilobytes as 1024, that means 2 to the power 10 bits, 2 to the power 10 bytes, and 1 megabyte is represented by again 2 to the power 10 kilobytes, that means 10 to the power 2 into 10 to the power 10 bytes. Again gigabytes, that means 2 to the power 10 multiplied by 2 to the power 10 multiplied by 2 to the power 10 this bytes. Now next come to octal number system. As I told you, octal number system has its digits from 0 to 7 and its positional weightage is taken in 8 to the power form. So 8 to the power form, this is represented as least digit and this is represented as most significant digit. So in this case we can say least significant digit, least significant digit, and this is taken as MSD, that is most significant digit. So this can be represented like this in octal number system. Now next is hexadecimal number system. In this the values are taken from 0 to 9 as numeric value, and from A to F it is taken as alphabetical values. So it can be again taken as in the positional weightage multiplication form, that is 16 to the power 0 is again LSD, this is the low significant digit, and this is the MSD, that is most significant digit. So decimal equivalent of hexadecimal number is given by, this is the number, its decimal equivalent is taken as 2 multiplied by 16 to the power 7 multiplied by 16 to the power, and this is taken in the positional weightage, this is this plus 15 multiplied by 16 to the power plus 10 multiplied by 16 to the power. So this can be taken in positional weightage form. Now next, if we take, so these are the different number system. If I will take the other number system, if I will take the other base number system, let's say other base number system X, let's say it is 7. So the digits will be allowed from 0 to 6, and the number decimal equivalent to 7 base system, decimal equivalent to 7 base system can be taken as, if let's say 7 base number is 256, this is the 7 base number system, and how I would convert this into decimal number. These numbers 2, 5, 6, they will be multiplied with their positional weightage in 7 base system, and positional weightage is taken from 0, 1, 2, and after that this will be added. So the final number we will get is, this will be added, and after addition we will get the final value which is equivalent to decimal number. So in this way, other system base can be calculated. Now next we are going to see the conversions between these numbers. Conversions. So for conversions, there is a technique or method. Decimal number system is the standard number system. So from for conversion, decimal number system, if we need to convert it into binary number system, and if it is converted into octal number system, hexadecimal, and other ways, it has same procedure. So first we will going to study about the conversion from decimal to other number system. So it has same method. Let us start with some example. If I am taking the example of decimal number system, let us suppose I am taking this number as 72.125. This is the number I am taking in decimal number system. I have to convert this into binary number system. So how should I convert? First of all, the method is, this number, this decimal number has basically two parts. One is integer part, and to the left of decimal is fractional part. So these two have different procedure. For integer part, we have to convert by factorizing the number with their base. So if I have to convert this number into binary, so binary has the base 2, binary has base 2, so it will be factorized by 2. If suppose if I will have to convert this number into octal number, I will going to factorize it by 8. And let's say if suppose it have to convert into 7 base system, it will be divided by 7. So I am going to divide it by 2 because I need to convert this into binary number. So for binary conversion, we have to factorize by 2, and this column represents quotient and this column represents remainder. So it will be divided by 2. So I will get the quotient as 36 and remainder as 0. Again, if I am going to divide, I am getting the quotient as 18 and remainder will be 0. Again, I am going to divide by 2, quotient will be 9, remainder will be 0, remainder will be 1, remainder will be 0, remainder will be 0. After this, last, if I am going to divide the 1 with 2, I get the remainder quotient as 0 and remainder will be 1. And the rule is to take the number in bottom to top approach. So the number will be taken from bottom to top. So the 72 in integer value represented as 72 integer value is represented as, it is taken from bottom to top to 1001000. So this is the equivalent binary number of decimal digit. Now the next method, how to convert the fractional part into binary number or any other base system. So as I told you, integer part will be factorized by the base. That is, if I have to convert this into binary, it will be divided or factorized by 2. Same as fractional part will be multiplied by the base. So fractional part, if I am taking 0.125, it should be multiplied by 2. So it is taken as, it is coming out to be 0.250 here. So its output or its binary equivalent number is taken from integer part. This integer value is coming out to be 0 here. So I will take the 0. Again multiply, again take the fractional part 0.250, again it is multiplied by 2. I will get 0.500 and the same integer value is coming out here is 0. Again the fractional part will be multiplied, 0.500 multiplied by 2. I will get 1.00. That means it is coming out to be 1 here. Now in this case we had observed here, fractional part now becomes 0. So the procedure is to multiply the fractional part with the base until the fractional part becomes 0. And after that I will take this number in binary equivalent form from top to bottom approach. So it will be taken as 0.001. So this is the complete binary conversion of 72.125. The other condition is if it is not 0. If it is not 0, then in that case I have to observe the repeating condition of digits. So it can be taken as repeated numbers, or otherwise if it is taken as repeated numbers, then bar will be taken over the digit, bar will be taken, otherwise up to 5 decimal place we can take the number. This is the condition if it is not arrived 0. So this is how we convert the decimal number into binary. In the same way, we can convert decimal number system into other number system. The difference is only the base will be changed here. So integer part will be divided by, if let's suppose it has to convert into hexadecimal, I can divide it by 16 or factorize by 16, and in the fractional part it is multiplied by 16. So this is how we can do the conversion from decimal to other number system. Now this is the procedure how to convert the decimal number system into other system. Now next we are going to learn about the conversion from other number system to decimal number system. Binary, octal, hexadecimal and other base system, if I need to convert it into decimal number system, it has again follow the same method. So for this we have require one method. So let us suppose I will take the example of binary number 101011. So I will get this number, this as 101. Now if we are going to convert this into decimal number, what I have to do? This is the decimal and their bits or digits are multiplied by their positional weightage. So in this method we are going to see that for any number system, if we have to convert it into decimal number system, we have to multiply each digit by their positional weightage in a certain manner. So in the left side, if we write the positional weightage, in the left side I can write its positional weightage is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. And the right side of the decimal, it can be written as 2 to the power minus 1, 2 to the power minus 2 and 2 to the power minus 3. So by multiplying each digits by their positional weightage, we can convert any other number system into decimal number system. So if we multiply and then add 2 to the power 5 plus 0 multiplied by 2 to the power 4 plus 2 to the power 3 multiplied by 1 plus 0 multiplied by 2 to the power 2, 1 multiplied by 2 to the power 1, 1 multiplied by 2 to the power 0 plus 1 multiplied by 2 to the minus 1, 0 to the minus 2, 1 multiplied by 2 to the power minus 3. So if you solve and add, we will get 32 plus 0 plus 8 plus 0 plus 2 plus 1 plus 1 divided by 2, that is 0.5 plus 0, 1 divided by 8, that is 0.125. So by adding this we get 43.625. This is the decimal equivalent number of the given binary number. So this is how we can convert other number system into decimal number system. So these are the two methods for interconversion of any number system into other system. Now let us suppose if I have to convert inter number system, like if I have to convert binary number system into hexadecimal number system, then in this case I need to first convert binary number system into standard number system, that is decimal number system. After this I can reconvert it into decimal number system. So this is how we follow the path. First I convert binary into decimal, then decimal to hexadecimal, and we follow the same methods for binary to other system to decimal conversion, we follow the same method, multiply by weightage, multiply by weightage, multiply by weightage of number system. If it is binary, then it is multiply by the weightage of 2 to the power. And if I have to convert decimal to hexadecimal, then for integer part factorization have to done, factorization by base, and for fractional part multiplication has to done. Now next, there is some method to convert the binary number into hexadecimal and octal number system. There is some table we follow. So first we are going to study the table for few decimal numbers to convert it from decimal number to binary for certain digits. So if we convert the 0 decimal number 1, 2, 3, 4, 5, 6, 7, 8, then after this is the another same table. So for this 0 conversion, we have certain code. If I want to represent any number, suppose I want to represent 2 in binary number, I require certain number of bits. So for only 2 numbers, if I have to represent two numbers by 1 bit, so we have only 2 digits, 0 and 1 combination possible. If I require 2 bits, 2 to the power 2, then I can represent 2 to the power 2, that means 4 numbers I can represent in the binary number. So similarly, if I require 3 bit, from 3 bit I can represent it in 8 numbers. So 8 numbers can be represented by 3 bit. So similarly, if I have to convert binary number into octal, I require 3 bits. Similarly, for 4 bit, that means conversion from binary to hexadecimal, I require 4 bits. So by keeping this into mind, I can form this table. There is a shortcut method. Binary weightage will be start from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So maximum, if I am taking 4 bit, for 4 bit there is 16 combinations possible from 0 to 15. So we can have a counting from 0 to 15. And each number has a weightage. This is 1, this is 2, this is 4, 8. So this is a 4-bit code. From this we can make the table. So for making the 0, all 4 bits, there is no 0. So we will keep 0, 0 in all the places. 1, for 1 I can put the logic 1 and remaining logics are 0. For 2 I can keep the logic 1 corresponding to 2, remaining logics are 0. For 3 it is a combination of 2 and 1. For both that combination I will put the logic 1 and remaining will be 0. So in this way a table will be formed as a counting. So this table can be referred for the conversion from a binary to octal or octal to binary. This is the table. So this table can be shown here. This is the table I can form. So by forming this table, by keeping this table, I can convert the binary number directly into, either it can be converted into octal number or hexadecimal. Or we can also have interconversion between octal and hexadecimal. So if we see the example how we can convert this octal number into hexadecimal, so we can take the example. Let us suppose take one again binary number 1010 1110 1 0 1 1 1 0 1 1 1. So if this is a binary number, if I need to convert this into hexadecimal number, so for converting the binary number into hexadecimal number, I have to form the group of 4 bits. Why group of 4 bits? Because hexadecimal requires 16 is made from 2 to the power 4 combination. That means 4 bit will be required. And if I need to convert this into octal number, I will require 3 bit. So this this we convert into group of 4s. This group of 4 I will take this group of 4 for the from the left side of decimal, and to the right side of decimal it will be taken in the group of 4. So this can be taken as 0 1 1 is 5, this is 7, this is 5, this is 1 1 0 1, that means it is 13. 13 is represented by D. This is 1 1 0 0, that is 12. 12 is represented by C. So this will give you the hexadecimal number. So in this way interconversion can be possible. So this will be enough for this lecture. So this I hope you will understand about how the conversions will be made by different techniques. So many more techniques can be discussed in the later slide.